Okay, welcome back. And so what we're going to do this time is we're going to do some multi-step calculations and learn how to correctly round the answers to the correct number of significant figures. And this is covered in 1.6 in your book. And then the last thing I'm going to talk about is the difference between accuracy and precision of measurements. And so let's get right to order of operations. So let me show you sort of what the problem we're facing is here. So let's say you have a multi-step calculation like this. And so you can see that in parentheses there is a subtraction followed by a division and then an addition of a number with an exponent. So the question you might ask yourself is, what do I do first? Do I do the addition first? Or do I take that number to the exponent first? Or do I do something in the parentheses first? And so the way you sort of know how to do these operations in the correct order is maybe you can sort of remember this abbreviation called PEMDAS. The mnemonic for PEMDAS is please excuse my dear Aunt Sally, and that will tell you the order in which you do these operations. So the first thing you want to do when you encounter a bunch of operations in an equation is to find any parentheses and do the operation within the parentheses. That is what you first do. And the next thing you would want to do is you want to deal with the exponents next. And then next thing you do is you do either multiplication or division. Now you don't necessarily do multiplication before division. What you do is you do multiplication or division in the order in which you encounter them in the equation. So division could be first, you do that first. Then you do addition or subtraction. Again, you don't always do addition before subtraction. You do them in the order in which you find them. So let me give you some examples of how to go ahead and solve these problems and doing these in the correct order of operation. So you see 2 times 8 divided by 4. And so what you see there is a multiplication and division. And so with the rule of multiplication and division, you do the one that comes first. And so there, multiplication comes first. And so here what we want to do is multiply 2 and 8 is 16. And then you do the division by 4. And so the answer you get is 4. Okay, the next problem, you have 8 divided by 2 times 3. Again, when you have multiplication and division, you do the one that comes first. And so here you're going to take 8 divided by 2 because that is first from left to right. And so that is 4. And then you multiply by 3. And so the answer should be 12. The next one, you have 7 minus 3 and then in parentheses 4 minus 2. So remembering PEMDAS, first thing you have to do when you have several different kinds of operations like this is you do what's in parentheses first. So here it would be equal to 7 minus 3. And then let's do the parentheses first. So what's 4 minus 2? It's going to be 2. Now what's next? So you have 7 minus 6. You have to do the multiplication there first between 3 and 2. So that's next. So it's 7 minus 6. And so the answer is going to be 1. Okay, and for the last one there, the first thing we want to do there is the exponent, so it would be 6 times 5 minus 3 times 16. Now you see a multiplication, then a subtraction, and then another multiplication. So what you should do is the multiplications first before you do the subtraction. So you have 6 times 5, that is 30. And then you don't do the subtraction yet. What you first do is multiply 3 times 16, which is 48, and then you do the subtraction, and 30 minus 48 is negative 18. Okay, let's move on. Okay, so now we need to figure out how do we deal with multi-step calculations in the sense that you're going to have to find an answer and get it to the correct number of significant figures. So again, let's say you have a multi-step calculation like this. And so we already learned how to deal with the operations and what order we do them in. So the next thing you need to figure out is how do we make sure that the answer is in the correct number of significant figures? And there's some important guidelines here. So the first guideline is to avoid rounding errors in multi-step calculations. round only the final answer. Do not round intermediate steps. For an intermediate step, which you'll get, write down the full number that the calculator gives you. The next guideline which is useful is when you write down intermediate answers, keep track of significant figures and also underline the uncertain digit. And then finally, when you get to the last operation in the last step, that operation rather than other operations which you may have previously done dominates. So in the last step, you have a final operation. You use those rules for significant figures that you learned earlier and use them for that operation. Okay, so here we have 3 problems that we can go through, and what we're going to try to do is find what the correct number of significant figures is for that final number you have in each of those problems. So for the first problem, we're taking 24.6681 multiplied by 2.38 and then adding 332.58. So I'm kind of hoping you learn that when you see those operations of multiplication and addition, you do the multiplication first. And so if you multiply 24.6681 by 2.38, the answer you get on your calculator is 58.710078. So you should keep that in your calculator. However, you should note how many significant figures you have in that number, considering the fact that you just did a multiplication and you might apply the rules of significant figures for multiplication. So let's figure that out right now. So that first number there has 6 significant figures. That next number has 3 significant figures. So you might remember for multiplication that you want to round the number to 3 significant figures. And so we indicate here that these first 3 digits in that number are significant, and I'm going to put a bar over the 7 here to indicate that that is an uncertain digit. That full number will be in your calculator, and then next you'll add 332.58, and you'll get that answer, that final answer of 391.290078. That will be in your calculator. So the question is, what is the answer in the correct number of significant figures? This is what you do. You remember that for the last operation you're doing here, which is addition, you apply the rules of addition to round that answer to the correct number of significant figures. And so the rules of addition look at the location of the uncertain digit, and you might remember that you round your answer so that its uncertain digit is in the same position as the leftmost in the measurements. So in 58.710078, there are 3 numbers that are significant, but the 7 is the uncertain digit. With 332.58, where is the uncertain digit? It looks like the 8 there is the uncertain digit. So we have an uncertain digit in one measurement in the 10th place. We have it in another measurement in the 100th place. And so what we need to do is round that number there, 391.290078, so that the last digit will be in the 10th place. And so what we do is we look to the next digit over, and we can see that it is above a 5. So we want to round the 2 up to a 3. So the answer should be 391.3. Okay, for the next problem. So you might remember from learning the correct order of doing operations that we do the subtraction in the parentheses first. And so if you do that, you will get 63.811 on your calculator. Now, let's indicate in 63.811 which numbers are significant from that operation you just did and what would be the estimated digit, even though you're not going to round the number. Okay. So here we have a subtraction that we're doing first, and so we apply the rule for subtraction. There's an uncertain digit here in the 10th place with the first measurement, and then we have an uncertain digit in the 1000th place in that next measurement. And so what we want to do is, if we were going to round 63.811, I'm hoping you'll know at this place that you would round to the 10th place. And so what that indicates here is if we were to round, we would get an answer with 3 significant figures. But again, this is in your calculator and you're not going to round it. Now, the last step is a division. The last step, we have to apply the rules of division for rounding significant figures. And so there, what we consider is the number of significant figures in the numbers we're dividing. So here in this last, in 63.811, we have 3 significant figures. On the next number there, 0.0059, we have 2 significant figures. And so since, again, this is division, we round the answer to the least number of significant figures, so it should be 2 significant figures. And so we're going to round here to 2 significant figures. We look at the digit in the next place over, and we can see that we need to round 0 up to 1. So the answer should be either 11,000 or better yet 1.1 times 10 to the 4. Okay, so the final problem, what we have is we have an addition and then we have it over another number, 63.498. Now, although it may not be so obvious, there's, again, a division there. And what you really have to do first is any divisions that you need to do before you do the addition. So you have 2 numbers and you're dividing it by a number in the denominator. The first thing you need to do is to divide each number in the numerator by that number in the denominator, which I have done. So 249.362 divided by 63.498 is that first number in red, 3.92708, etc. And then 41 divided by 63.498 is that next number there. So let us see at this point in those numbers where the significant digits are and where is the uncertain digit. Okay, so when you're dividing 249.362 by 63.498, it looks like there are 6 significant figures here. There are, looks like 5 significant figures here. And so since this is a division, what we would want to do is, if we were to round this, we're not going to, of course, but if we were to round this, we would round this to 5 significant figures. So we would round it to that place there. It looks like the 10,000th place. And so I indicate the 0 in the 10,000th place is the uncertain digit. Now, the next division was 41 divided by 63.498. So now you have 2 significant figures divided by 5 significant figures. And so we want to round this to 2 significant figures. And so this last digit here in the 100th place will be the uncertain digit. Now, the very last step is an addition. And so the rules for addition will dominate at this point. And the rule of addition suggests that you round your answer so its uncertain digit is in the same location as the leftmost uncertain digit of your measurements. So it looks like in our first number here that I'm kind of pointing to, we have an uncertain digit in the 10,000th place. And then in this next one, we have an uncertain digit in the 100th place. And so for our final answer, that's the number we get on our calculator, we really want to round that to the 100th place. So the answer should be 4.57. This is just kind of a reminder of what exact numbers are. Again, exact numbers are numbers that you know exactly. And so one of the questions you might ask is, well, if you encounter an exact number, how many significant figures are there? And so what's kind of important to know is that whenever you have an exact number in a calculation, you assume that there's an infinite number of significant figures. So for example, in a calculation, you might have a situation where you're dealing with the knowledge that you have 1,000 millimeters in 1 meter. And so you might immediately say, oh, we have 1,000 there, but you'll notice hopefully that there's no decimal place. And you might say, well, okay, there's no decimal place. So in that 1,000 number, in the 1,000 millimeters, there is only 1 significant figure. If you said that, that wouldn't be right. Because it is an exact number, you know there are 1,000 millimeters in a meter and not 998.2. Again, exactly 1,000 millimeters. Whenever you have an exact number, it has an infinite number of significant figures. So when you're dealing with 1,000 in a problem, you don't think of it as having 1 significant figure. because it's an exact number, you have to remind yourself that there are an infinite number of significant figures, and we'll deal with that later. Okay, next thing I'm going to talk about is the difference between accuracy and precision. So what accuracy is, it's a sort of a measure of how your measured value differs from the true value if it is known. So let me give you an example of sort of distinguishing between two measurements and trying to figure out which one is more accurate. Let's say you have a beaker of boiling water, and so you know that water boils at 100 degrees Celsius. So let's say you have a good thermometer, and the good thermometer measures the temperature of the water, and it measures it not to be exactly 100.0 degrees Celsius like it should be, that is the true value, but it measures it to be at 100.4 degrees Celsius. But let's say you have a not so good thermometer, a bad thermometer, and let's say you measure the temperature with that, and it gives you a value that's even further off. And so it measures what should be 100.0 degrees, it measures it to be 103.7 degrees. So the question is, which thermometer is more accurate? So you kind of already know that maybe the one that measured closer to the true value is the more accurate. And so that would be the thermometer that measures at 100.4 degrees. So again, if you have several pieces of instrumentation and you're trying to make a measurement, you know what the true value is. The instrumentation that gets you closest to the true value is the more accurate one. So you can sort of evaluate that quantitatively in a couple of ways. So one way you can evaluate accuracy is just simply subtracting the measured value from the true value and seeing what the difference is. And so with the mercury good thermometer, we got a measurement of 100.4 degrees Celsius, and the true value is 100.0 degrees Celsius. And so the difference between the measured value and the true value is 0.4 degrees, which is reasonably close. With the cruddy barometer, I think is 103.7 is what we measured to be, and the true value is 100.0, and so here the difference is 3.7 degrees Celsius. And so in this simple fashion, we can sort of evaluate which instrument is more accurate. Is going to be the good mercury thermometer because it has the lowest difference between the measured value and the true value. So this measurement you're making to evaluate accuracy is called error. And again, error is just simply the difference between the measured value and the true value. Another way you can evaluate how close your measurement is to the true value is you can do it by percent error. So percent error, as I kind of indicated there, is just the error divided by the true value times 100. So what we're going to do is calculate the percent error for these two thermometers. And so with one thermometer, the good one, our error value was 0.4. We're going to divide by the true value, which is 100.0 degrees Celsius, and multiply by 100. And if you work that out in your calculator, it's going to be 0.4%. And so with the alcohol thermometer, the cruddy thermometer, the error that you got was 3.7 degrees divided by 100, the true value, times 100, so it should be 3.7%. And so again, this is just sort of another way of evaluating how close your measurement is to the true value. And so the higher the percentage, the less accurate your measurement is. So now what we're going to do is talk about precision of measurements. And so this has a definition that's a little bit different than what we were talking about before. So what we were talking about before is where precision sort of judge how many decimal places that you can make a measurement to. We're not really going to talk about that anymore, and that's not going to be on your test. Rather, we're going to talk about precision in a different way. Precision now is if you make a bunch of measurements at the same time, you're judging how close the measurements are to one another. So I think the best way I can sort of describe that is with a simple example. Let's say you have two balances, and so we have balance A and balance B. And let's say you throw a penny 5 times onto each balance and record a number that you get. So let's look at balance A first, and let's see the variety of measurements you get from balance A. And so what you can see is that there's a pretty good range of numbers you might get. So the lowest measurement for mass of the penny appears to be measurement number 2, which is 2.992 grams. Yet we get a measurement which is higher than that, or measurements, they're all higher than that, but the one that is the greatest is measurement 4, which is 3.036 grams. So that's a pretty good range of values. And so it looks like to me what we have is about 0.044 range of values. Now with balance B, you can sort of look at the numbers immediately, and when you threw the penny 5 times into balance B, what you can see is that these measurements are closer together. And so here we know that is because the range of values is far less. And so here the range of values range for balance B from measurement 1, 3.003 grams, up to 3.012 grams. So it looks like a smaller range of values you got. And so it's 0.009 grams. And so I actually indicated here what the ranges of the measurements you got for each balance A and B. Another way you can judge that range of values is with something called standard deviation, which we're not going to talk about today. But anyway, the more precise instrument is the instrument which gives you the most narrow range of values. So what I'm kind of hoping you'll see is that scale B gives us the narrowest range of values and therefore would be considered the more precise instrument compared to scale A. So as a next to final slide, let's kind of look at this in sort of a qualitative way. And so let's look at these bullseyes here. And so I want you to think of the red dot in the center of the bullseye as the true value and the arrows as the measurements. And so I want you to figure out, when you're looking at those arrows as measurements, are those measurements accurate or not, or are they precise or not? So if we look at the top left bullseye, it looks like all the measurements are landing pretty close to the true value. If that is the case, then that is a relatively accurate measurement compared to maybe those other bullseyes, and those arrows are falling pretty close together. And so if that's the case, then the arrows are relatively precise, and so that is very precise and accurate. Now, if we look at the right target, you can see definitely it's not as precise because the arrows are further apart from each other, but they're still on average close to the target. So I would say on the right target, they are less precise, but they are still accurate. Okay, in the lower left target, what you can see is that the arrows are no longer near the true value. If that is the case, those measurements are no longer relatively accurate, but the measurements are close to one another. And so if that is the case, they are relatively precise. So it looks like for the bottom left, I would say it is precise, but not accurate. And then the final one, it looks like the arrows are way off from the true value, and they're not close together, so it's not precise or not accurate. And so the final question I have for you is this. Water freezes at 0.0 degrees Celsius, and it's measured with 3 different thermometers, either thermometers 1, 2, or 3 at 5 different times. So the thermometer number 1 is measuring it 5 times, and those measurements are A through E. Thermometer number 2, you're measuring it 5 times F through J. And thermometer number 3, you're measuring it 5 times K through O. So of these 3 thermometers, which are the most accurate and which one is the most precise? So let's go ahead and deal with accuracy. What I'm kind of hoping you remember, accuracy doesn't so much refer to how close the measurements are to one another. That would be precision. Accuracy refers to how close the measurements are to the true value. So the true value is 0.0 degrees, and so we want to find a group of measurements that seems to be relatively closest to the true value at 0.0 degrees. So if you look at these carefully, thermometer number 2, you can see that all those values that we got are around 3 degrees, which is kind of far off from 0 degrees, so that is probably the least accurate. Thermometer number 1, they all are closer to 0.0 degrees, but most of the measurements trend in the negatives. Maybe the average there may be something like, I don't know, negative 0.5 degrees. That's closer to the true value of 0.0 degrees. And with thermometer 3, there you can see that the measurements are hovering around 0.0 degrees. And so it looks like thermometer 3, when you average all those numbers together for the measurement, will give us an average that is closest to the true value. So I would say thermometer 3 is the most accurate. Okay, which one is the most precise? So the most precise is the thermometer that gives you a group of measurements that are as close together as possible. They don't necessarily have to be accurate. They just have to be close together. So if you look at thermometer 1, thermometer 2, and thermometer 3, what you can see is that thermometer 2, it looks like it has a bunch of measurements that are very close together. They're all close to 1/10 of a degree. Now, it's not very accurate. It's not close to the true value of the temperature of the water, which is 0.0 degrees, but that is not important. We're just looking for the thermometer that gives you the measurements that are all closest together, and so that thermometer will be the most precise thermometer. So thermometer 2 is the most precise. Thank you for listening to all that. My handwriting will probably improve, so we'll talk to you later.